is Stefano Facchini, and he will talk about observables of inner disks dynamics.
Thank you, Antonella, and thank you to the organizers for having invited me here to give this talk. In order to start, I'd like to highlight this sentence that we're reporting in the abstract for this conference. And to me, again, one of the idea why these UXOR and these photometric behaviors of young stars are very interesting is because they are a unique probe of the dynamics of the very inner system, which is usually inaccessible by direct imaging. Mike. Prova. And regions that are usually inaccessible by, for example, imaging. And the timescales are fast enough that we can really probe the dynamics of the very inner regions of the sub-EU scale. And one of the reasons because which is interesting per se, but as we know, most of the exoplanet population we are seeing is really located in the inner regions, in particular in the, sorry, this is not popping out very well, in the inner 1AU that again, we usually probe via photometry or with spectroscopy. But today I'm not going to talk about photometry or spectroscopy, but I am going to talk about imaging. And the reason is that since kind of this paper came out, we started realizing that the outer disk can actually probe what's happening in the very inner scales of the disk, even sub-AU scales. When this image came out, everybody was puzzled how to explain these strong shadows that we see in the scattered light image of the HD 142527 system. And 1 year later, Seba Marino and collaborators came out with this radiated transfer model where if you inject a misaligned inner disk, as we've heard in the previous talks, in the inner disk, this is going to cast a shadow along the line of nodes in the inner disk. And you can reproduce the data that you see in this top left panel with a model where with the highly misaligned inner disk by about 70 degrees or so. So again, we can use these large scale, let's call them images, to probe what's happening in the inner regions. And how is it possible dynamically to obtain a misaligned inner disk? This is just an example. Here you don't see there is a binary you can think of as spectroscopic binary in the very inner regions that is misaligned by 6 degrees with respect to the outer disk. You just let gravity and hydrodynamics play their role, and what you get is that if the torque of the binary onto the disk is strong enough, the disk is not able to communicate to the outer region, that it has to follow the inclination of the binary, and the disk breaks. So this is called disk breaking mechanism. This is just one example with a circumbinary disk case, but what this tells us is that if there is a strong enough torque in the inner regions, the disk can break, and the inner disk can precess independently from the outer disk, and they become almost detached. And if you take one radiated transfer model, if you do the radiated transfer on one of those simulations, you see that you can get highly misaligned systems with sharp shadows, or if the misalignment is less pronounced, let's say 30 degrees, you get that half of the disk in scattered light is expected to be shadow from the inner regions. And you can see a kind of a sketch of what you expect down here. And what's interesting, again, that after we ran the simulation, this data came out. Actually, we saw this data of the HD 143006 system. And what you can see is that the west part of the disk is totally shadowed. There are 2 dark lanes here, as in the model, and that's because we think there is an inner disk that is misaligned by 30 degrees or so with respect to the outer regions. And again, this is another image with the shadows we already heard about that is probing what might be happening in the inner disk. Another example of broad shadows, sorry, Antonio should have removed this slide, but it's seen, so I'm going to talk about it, is this other system where more than half of the disk is in shadowed, and we had some difficulty in interpreting what we see because if there is a misaligned inner disk, you expect to have at most 180 degrees of shadows onto the outer regions. So in order to model it with a simple radiated transfer model, we had to require to have at least 2 rings that are misaligned with respect to each other, which are again misaligned with respect to the outer disk. So a kind of crazy system, but you see that in this way, the model is able to reproduce the big shadow here and the azimuthal asymmetry that you see in the very, very inner disk. I've talked about scatter light, but there are other tracers we can use. If you take the same simulations I showed earlier and you do a radiated transfer of dust continuum at millimeter wavelengths of gas, you also expect to see shadows in the sub-millimeter, even if less pronounced, because these are a thermal effect and are not an illumination effect. You also expect to see strong twists in the kinematics. And one case in which almost all of this has been seen is for J1604, where here you see the scatter light image. We have shadows along the east-west direction that are also have a counterpart in the sub-millimeter continuum. We have shadows in the CO, so the temperature structure of the gas is tracing the illumination pattern that the disk receives from the inner regions. And there are also hints of this kink in the kinematics that is telling us that the inner disk might be indeed warping in the inner regions. Another example is CQ tau, since I added this slide as we talked, as you talked, since we have heard a lot of about it in the very inner first talks. This scatter light image with a lot of structure, possible shadow again, and this is the sphere image in high-pass filter. So when you really pump up the fine features, and what we see is that there is a lot of structure in the disk, and whether these UXORI objects, when you image them, are highly substructured, for example, that's a question that I'm not sure we have an answer to. But if this is the case, it might tell us that there is a intrinsic link between what's happening in the outer disk and what's happening in the very inner disk. And this is not unexpected because you have accretion phenomena or misalignment, for example, which is again related to accretion, that is connecting the very two different scales. And here another, to show, again, CQ tau, another hint of substructure is the kinematics. You see that this is the, what we can call moment one map, so the kinematic structure of the disk. And you see that the isovelocity curves are highly bent. And that might be tracing, again, a warp or radial inflows towards the inner region. So theoretically, the question is, we think there is misalignment. So what is driving it? There are at least 3 possible solutions. One of them is that we have a substellar companion inside the cavity, and this is the case, for example, for HD 142527, the famous disk I showed at the beginning. This is known to have a highly eccentric 0.2 solar mass secondary star. The primary is about 2 solar masses, which is probably driving all the spiral feature you see, the huge cavity, and also misaligned in the inner disk. Dan Price had a good model of the disk in this paper. And so the question is, how many of these disks showing shadows and misaligned inner disk might have a hidden substellar companion that we haven't seen yet, because it's very close to the central star? We're almost blind to the inner 10 AU from the star with direct imaging, usually, because of the coronagraph. So I think we really, observationally, we should really push this as much as we can with current instrumentation. Another possibility is misaligned planet. There are these nice simulations and models by Zhao Wanzhou, where it showed that if you have at least one Jupiter mass planet that is misaligned, it creates a gap. It can disconnect the inner and outer regions of the disk, and the inner disk is expected to follow the inclination of the planet. If the angular momentum of the inner disk is lower than the angular momentum of the planet itself. I'm showing this. So the planet hypothesis is clearly exciting for many, because when we hear planets, everybody gets excited. We're now at a stage where we are hopefully managing to get signatures of planets within the cavity of transition disk, massive planets. This is a famous PDS-70 system where we image with Sphere and Muse and maybe ALMA, something that is tracing the presence of two massive planets. And why am I saying this? Because theoretically, one important question is how much mass can filter through the cavity that is opened up by planets or couples of planets. And to answer this, we have to connect what's happening in the very inner regions, so photometry, spectroscopy of the star itself, with what we see in these images. And to me, this is a very big question that hopefully we can try to constrain much better observation in the near future. Another theoretical game we can play is these shadows move, and I was mentioning also this morning, and in the hypothesis that what is driving the shadow, it is a planet. There is a quite simple semi-analytical relation with which we can link the precessional period of the shadow, so the movement of the shadow, which is tracing the precessional period of the very inner disk, with the mass of the planet, if we know the location of the planet. But we kind of know if we see the gap. And that's simply the orbital period of the planet with the ratio of the mass ratio of the planet to the star. So for a planet with 1 year orbit and the planet is 1 Jupiter mass, the precession period is expected to be roughly 1,000 years. And interesting, shadows do move. This is an example of TW Hydra. These are two images taken with HST. And if we look at how much the shadow moved as a function of radius, this is the difference of the position angle.
Where is the shadow?
So here it's not a sharp shadow, but you can see that this side of the disk is less bright than this side. Okay. And here, again, this side of the disk is less bright than this side.
So I have to look at how the bright side moves.
Exactly, how the bright side moves. And he has moved by roughly 17 degrees in 10 months, which is quite fast. So whatever is projecting the shadow has moved by 17 degrees, or maybe 377, we don't know. But again, this is something with which we can link the outer disk to the inner disk and try to understand. And Rebecca Nealon had a paper on this where they managed to reproduce the shadowing itself in one snapshot with a massive planet, but it doesn't match with the velocity at which the shadows are moving. So there are inconsistencies here. And finally, something that I'm sure will come back a lot during this conference, but I'm not going to mention much, is that at least for less massive stars, where they're mostly convective, we expect the magnetic field to be mostly dipolar. And if the magnetic field is misaligned with respect to the disk, we expect the magnetic field to warp and misalign the very inner regions. And this theoretically has been proved. And while I don't think it can explain the misalignment we see in Herbig stars, it might be a good candidate for what we see in T-Tauri stars, so in later type stars. So my final, I'm almost done. So theoretically, I think there is something that we really should work on, because everybody invokes misaligned planets when they see a shadow. I don't know if there are planets in there, and I don't know if they're misaligned. But theoretically, we have a huge problem that we don't know how to get them misaligned. So, and no one is really looking into this, in my opinion. There was some people in their introduction mentioned planet-planet scattering, but I haven't seen any simulation where a planet can be scattered out. where still a lot of gas inside the disk scattered out from the orbital plane. Something that to me can be very exciting is that we know that in the very inner phases of disk formation, the disk does change angular momentum because the accretion from the star-forming regions onto the disk is highly chaotic, like in these simulations by Matthew Bate. If planets form very fast, let's say within the first 10 to the 5 even years, what can happen is that you have accretion onto the disk that changes the angular momentum, but the planet doesn't react to it because it doesn't feel the drag of the gas, and you get a system where the disk is misaligned with respect to the planet. And this can happen if planet formation occurs very rapidly, which might be. And finally, we have more evidence that in some systems there are late phases of accretion from the surrounding material. This amazing image of, I think it's SU Auriga, where we see a filament from the cloud that is feeding the disk. You can see a strong twist in the very inner regions, so the disk is responding and changing its angular momentum. Final 2 slides. I know there will be many talks on RW Auriga, but here I mostly mention how we can trace the inner disk using the outer disk. But the question I also have is, can the dynamics of the outer disk affect the very inner regions, not just through viscous evolution, for example? And to me, this is a splendid candidate. RW Auriga will here, that's a UXORI object. It started undergoing some episodic dimming by about 3 magnitudes in V band since 2010 or so. And we have taken a couple of spectra. We can probe the properties of the dust that is occulting the star during dimmings. But what we always have to keep in mind is that if this system, if we look on large scales with ALMA, this about 7 arcsecond across, the system is a binary. We see a primary component here, A, B. This is a moment of the intensity of gas into LCO. And there is this huge tidal tail that is trailing the primary disk that is sign of a flyby that has recently occurred. And we did some modeling of this back in 2015, where the secondary didn't have a disk. And indeed, you can reproduce the system by using this kind of flyby models. If we zoom in even more, these are data I looked at last night. So sorry for not removing this noise. Remember the image I showed here, this about 7 arcsecond across. And so we're really zooming in these inner regions. And this map is about 2 arcsecond across. Here we see the inner disk, that is the primary disk that is very well resolved. And you see that there is the secondary spiral coming out from the disk. And there is the first spiral that is then connected to the large scale. So this disk is being highly perturbed by the encounter. If you do some math, we know when the encounter roughly happened. And if you compute the time from the interaction to when the flash of material should be accreted onto the star, this time should be roughly now. So to me, this is at least interesting. I'm not saying this can explain RW Auriga. We know it's much more complicated than this. But it might be that the very inner disk is responding to the large-scale encounter that occurred about 500 years ago, and which is traced by these spiral structures. And again, to me, this is an amazing way to connect these scales to the photometric behavior of star. To conclude, because I'm late by 1 minute, sorry, Antonella.
Not challenging.
Okay. Instead of summarizing my conclusion, I end up with some questions that I have, at least, both theoretically and observationally. So the question in terms of the Herbig stars, and particularly the ones that show shadows, how many of them are hiding a substellar, let's say brown dwarf companion in the very in the inner AUs that might be responsible for the shadows we see. If these inner regions are misaligned, what's the effect of this misalignment in terms of planet formation? That's something no one has really seen. If this is a common feature. And then what are these varying shadows tracing? We don't really know, I think. That's my opinion. And finally, theoretically, as I mentioned before, how can a massive planet get misaligned? I think there is a lot of work to do, and it would be very nice to see one. I'm not sure they exist, but if they do, we hope that in the future with new instrumentation, we'll be able to catch them. And with this, I'll conclude and take any questions. Thank you.
Opens many questions. Yes?
Yeah, concerning this hypothesis that unobserved planets could cause this misalignment in disk, has anyone compared the fraction of misaligned disk in premium sequence stars with the fraction of misaligned exoplanets in around main sequence stars? Because I don't think there are many misaligned exoplanets. Is that a problem of an observational problem or?
So not really. I mean, the non-massive planets, so if you think of, the super Earth chains, they're usually all aligned. It's also true there is a huge observational bias because we wouldn't see a misaligned one because usually these are eclipsing systems. But if you think of the hot Jupiters, we know there is a huge dispersion in the inclination and eccentricity. Whether that's due to scattering or to initial conditions that's still debated. These are measurements that are done through the Rossiter-McLaughlin effect. And there is a huge diversity of misalignment with respect to the stellar rotation axis. So they measure the misalignment of the star to the so the angular momentum of the star to the angular momentum of the hot Jupiter, and they also found counter-rotating objects. So something happened, whether it's planet-planet scattering or primordial, I don't know.
How do you know that these structures that you interpret as shadows, these are not actually vortices that you see in the disk? So if I look at one of these images, it looks like there is a vortex on the bright side, and it's not a shadow; it's a brightening on the other side due to a vortex.
Yeah, I haven't shown maybe the best.
Yeah, even here, if you go back.
So, for example, this one.
Yes, no, that's not the best example. If you go further, maybe this one, yes. Yeah.
I don't know. Tell me when to stop.
Later.
Yeah, this Secutal, I think in this one.
Sukita, we don't know if there is a shadow or not, but so forget about this.
On the left, to me, it looks like a vortex there.
Yeah, here it's probably a spiral.
There is a spiral, but that bright crescent side, it looks like a vortex.
This one here?
Yes. No, yes.
I think it's a spiral, but I mean, we're working on it. But if you deproject the image, taking account the inclination that we know we have from the submillimeter and the gas, then it doesn't look corradial, so it's probably a spiral. Here, I don't think it's a super good example for the shadow, but I mentioned this because the CQ tau system came out quite often during the first talk, so I added this slide. But in, for example, this case, clearly, this outer region is shadowed by something.
Yeah, but to me, it looks like it may be brightened on the other side. Why do you interpret it as being shadowed?
I mean, if you had some small dust here,
on the other side.
I mean, you can, I mean, scatter light, it's, I mean, then Antonio can comment on this, but it's a combination of density of grains and also the illumination pattern, and in this case also polarization, because these are our PDI images, I believe, with sphere. But in here, this is, Antonio, maybe you want to answer to me.
Yeah, I mean, in that case, we see structures really disappearing and then reappearing again, where you would expect this picture to be. So there's no physical way to explain it unless it's a shadow. It must be a shadow in most cases. And for this broad shadow, it's a little bit more tricky maybe, but I mean, current framework is that there's just no other way to explain it.
Same on this azimuthal asymmetries are also explained by velocity weight.
Yeah, but look, scatter light will just trace the illumination pattern. It's not really, I mean, if you have a vortex, I mean, you really have to have a major increase of the discal height in the disk in order to see the scatter light, because we're not sensitive to the bulk of the dust in the midplane, we're just sensitive to the scale height of the
It
data.
might be true because anticyclones have equal pressure in the center, right? So high pressure in the center would imply high scatter height.
Okay, that's fair enough, but then how do we explain the lack of scatter light on the other side?
I think we can at some point.
Yeah.
I understand the question. I also thought that if you see the precession of the two shades, like in some cases the period that they have, it tells you that is due to something which is much closer to the star.
Yeah, in J1604 they have variations of days.
Yeah.
So it cannot be outer
Or
disk.
anything which is at the location where we see the shade. But let's talk about. We will talk more about that. There will be more talks. Timo had a question before, so.
Just the RW Auriga, the 500 years, is it based on known orbit or is it based on simulation? And you said that then it should have happened 500 years.
We also have good astrometry now. We are also adding ALMA because it has a very good, at least relative astrometry, and we use that as an input for the model. Then the model seems to work, but we don't. So yeah, we have the astrometry to do it.
Yes.
I have two questions. One about RW Auriga. Is it a planar encounter?
We think it's not. In particular, the secondary has a disk that is misaligned and it's highly eccentric. I didn't show, but that's what it looks like when I looked at it last night. But I didn't manage to do a pretty image to show in the talk. But the two disks are slightly misaligned, I think.
And another quick question. It's about CPU tau. I can't see from here what the continuum is doing, what the ALMA continuum is like.
But it's difficult to say. I'm going too far. So it could be, so there is some arc here. Maybe there is an M=2 spiral, if you want to believe it. But this is, again, high-pass filter, so we should be careful. For sure, it is structured. There are some structures that look kind of the one in HD 100-546, where there is kind of two rings with a crescent in between. That's very weird.
There's nothing like the structure we see in scattered light.
No.
No.
No. Actually, if you see here, because these are different scales, sorry, I should have mentioned. This is scatter light, then I squeeze in the scatter light, and these are the contours of ALMA. And the scatter light is really, most of it is inside the millimeter continuum emission.
Yes, last question.
So following the question from Edward, so about whether that is a vortex or a shadow, so can you compare the azimuthal movement with the local Keplerian time scale? If it's too fast, then it needs to be the outer disk response to some change in the inner.
For the shadows, you mean?
Yeah.
Yeah, so we don't have so many moving shadows. The ones we have, though, are J1604. There is HD 135344B. These two are the ones I remember, and the shadows are moving much faster than the dynamical time, the orbital time scale where you see them. So they cannot be related to something that is happening in the outer disk. They have to be related to the inner disk.
So for that one, at least for that one, it cannot be a moving vortex.
No, they cannot.
Let's thank Stefano again. Thank you very much.